Hello students, hope you all are healthy at your homes. So in the previous lecture we were discussing the topic reflection and transmission at oblique incidence. So today we are going to continue the previous topic, that is reflection and transmission at oblique incidence. So in the previous lecture we have find the values of E0t, that is equals to 2 upon alpha plus beta E0i and E0r equals to alpha minus beta upon alpha plus beta. So these are known as Fresnel's equations. Okay, so these are Fresnel equations for the case of polarization in the plane of incidence. So the transmitted wave is always in phase with the incident one, and the reflected waves in either in phase. There is a right side up. So if alpha is greater than beta, then this is in phase. Okay, so if alpha is less than beta, then there is 180-degree phase difference. Okay, so the amplitudes of the transmitted and reflected waves depends on the angle of incidence, because alpha is a function of theta. So here alpha is equals to 1 minus sine square theta t upon cos theta I. Okay, because alpha is equals to cos theta t upon cos theta I, so by using the identity cos square theta plus sine square theta equals to 1, we can write cos theta t in terms of 1 minus sine square theta t. Okay, so this is the value of alpha, and we know that sine theta t is equals to n1 upon n2 into sine theta I, so it becomes 1 minus n1 upon n2 sine theta I whole square upon cos theta I. Okay, so in the case of normal incidence, we have theta I is equals to 0 for normal incidence. So in that case, when theta I is equals to 0, then alpha is equals to 1 and E0r becomes 1 minus beta upon 1 plus beta E0i, and E0 t is equals to 2 upon 1 plus beta E0i, which are previous equations which we have already find in case of normal incidence. Okay, so at the grazing incidence, that is at grazing incidence, that is theta is equals to 90-degree, then alpha diverges and the wave is totally reflected. Okay, So for polarization parallel to the plane of incidence, there is angle of incidence that is called Brewster's angle, for which there is no reflected wave. So according to our previous equations for E0t and E0r, this occurs only when alpha equals to beta. Okay, so in that case, sine square theta b equals to 1 minus beta square n1 upon n2 square minus beta square. Okay, so for a typical case where theta b is the Brewster angle. So for the typical case when mu1 is approximately equals to mu2, so beta is approximately equals to n2 upon n1, and in that case sine square theta b is approximately equals to beta square upon 1 plus beta square, and hence tan theta b is approximately equals to n2 upon n1. Okay, so if the plane wave of mixed polarization is incident on a plane interface at Brewster angle, the reflected radiation is completely plane polarized with the polarization vector perpendicular to the plane of incidence. So this behavior can be used to produce beams of plane polarized light. Even if we consider the unpolarized wave is reflected at angles other than Brewster angle, then there is a tendency for the reflected wave to be predominantly polarized perpendicular to the plane of incidence. Okay, so in this we have two phenomena. The first one is that the Brewster angle, and the second one is the total internal reflection. So the word internal implies that the incident and reflected waves are in a medium of larger index of refraction than the refracted wave. It is n2 is greater than n1. So Snell's law shows that if n2 is equals, sorry, it's greater than n1, then theta t is greater than theta I. So consequently, if theta t is equals to pi by 2, when theta I is equals to theta I naught, then where theta I naught is the angle of incidence, when angle of free friction is 90 degree, then theta I naught is equals to sine inverse n1 upon n2. So for the waves that incident at theta I is equals to theta I naught, the refracted wave is propagated parallel to the surface. So there can be no energy flow across the surface. So hence at that angle of incidence there must be total reflection. So if theta I is greater than theta I naught, then sine theta t is greater than 1. This means that theta t is a complex angle with a purely imaginary cosine. So in that case, cos theta t is equals to theta I root sine theta I upon sine theta I naught square minus 1. So the meaning of these complex quantities becomes clear when we consider the propagation factor for the refracted wave. So exponential iota kt dot x equals to exponential iota kt x sine theta plus z cos theta, and that is equals to exponential minus kt sine theta I upon sine theta I naught square minus 1 raised to power 1 by 2 into z into exponential iota kt sine theta t upon sine theta I naught into x. So this shows that for theta I greater than theta I naught, the refracted wave is propagated only parallel to the surface and is attenuated exponentially beyond the interface. So the attenuation occurs within a very few wavelengths of the boundary except for theta I is equivalent to theta I dot. And next, the power per unit area striking the interface is S dot Z cap. Thus the incident intensity I is equals to half epsilon 1 V1 E0 I square cos theta I. While the reflected and transmitted intensities are IR equals to half epsilon 1 V1 E0 R square cos theta R, and IT is equals to half epsilon 2 V2 E0 T square cos theta T. So now we're going to find the value of reflection and transmission coefficients for the waves as we or as we find earlier in case of normal incident. So R is equals to IR upon II. So that becomes E0 R square upon E0 I square, and this is equals to alpha minus beta square upon alpha plus beta square E0 I square upon E0 I square. So cancelling the common terms, what we get R is equals to alpha minus beta upon alpha plus beta whole square. Okay, so next transmission coefficient, that is T, that is equals to so here T is equals to IT upon II equals to epsilon 2 B2 upon epsilon 1 V1 E0 T square upon E0 I square cos theta T upon cos theta I. So it becomes alpha beta 2 upon alpha plus beta on putting the values of different quantities. So note here again R plus T is equals to 1. You can easily solve it by simply putting the values of R and T as find above. So R is the friction of instant energy that is reflected, and naturally it goes to 0 at Brewster angle, and T is the fraction of transmitted energy and gives to perpendicular at theta b, and R plus T equals to 1 as required with the conservation of energy. So the energy per unit time Reaching a particular patch on area on the surface is equal to the energy per unit time leaving the patch. Okay, so here is all that is this is all about reflection and transmission at oblique incidence. Have a nice day.